So hello dear students, welcome to Wallah, and today we are going to start the topic that is continuous time Fourier transform, and we'll be covering these topics today, that is the continuous time Fourier transform and its properties, Fourier transform of some important signals, and the inverse Fourier transform. So we'll be covering these three things. These are very important. This is a very important topic for GATE. Okay. And many a times the GATE has asked questions from this topic: duality theorem, Parseval's theorem. So we will be looking at all the properties. We will be looking at the Fourier transform of few signals, few important signals. Okay. So let's first of all see the basic formulas. What are the basic formulas of Fourier transform? There are two basic formulas. One is the formula for Fourier transform, and another is the formula for the inverse Fourier transform. Okay. So first of all, let's see the formula. The formula is, the Fourier transform is written as x omega. The Fourier transform of the signal is written as x omega. Okay. So x omega is equal to minus infinity to infinity xt e to power minus j omega t dt. Okay, and we know that when this formula is applicable, because in the starting of the Fourier Laplace transform I told you that this formula is valid only when xt is absolutely integrable, and the inverse Fourier transform formula is xt is equals to 1 upon 2 pi integration minus infinity to infinity x omega e to power j omega t d omega. So this is the inverse Fourier transform formula. So these two are the basic formulas. This is the formula for Fourier transform. This is the formula for inverse Fourier transform. Okay. So now let's move on to how to find out, like, what all are the methods to find out the Fourier transform. Like, it is not like directly we can apply the formula, because it is not useful, because we have already studied Laplace transform. So we will use that concept here. So there are two methods to find out the Fourier transform. There are two methods to find out the Fourier transform. Method number 1 and method number 2. So first of all, I'd like to tell you that Fourier transform can be found in chapter number 1. We have studied three types of signals, that is energy signal, power signal, and neither energy nor power signal. Okay. So Fourier transform can be found for power signals and energy signals only. It cannot be found for the neither energy nor power signals. Okay. So remember this, that the Fourier transform can be found for only energy signals energy signals are those okay. So we have two cases. One case is energy signals, another case is the power signals. Okay. Another case is the power signals. So for energy signals, we don't need to actually find out the Fourier transform, because we can directly apply the Laplace transform and replace s by j omega directly. So the method is, we simply find the Laplace transform of the signal and replace s by j omega. Okay, replace s by j omega. This is the method for the energy signals. Okay, and for the power signals, the method is duality. So I'll tell you what is duality. So the method is we cannot apply the formula. For power signals, we will never apply the formulas. Okay. We will find out the Fourier transform using duality. We will not apply the formula. We will apply duality, and I'll tell you duality in this session itself. Okay. So we will apply duality. Okay. So let's find out for a few signals. So let's first of all see some formulas. Okay. Let's see the duality also, and let's see some formulas also. Fourier transform of few signals. First of all, let me tell you what is duality. The duality says that duality is like this. If xt is any signal and xt has Fourier transform x omega, xt has Fourier transform x omega, then duality says that if we replace omega by t in this expression of the Fourier transform, in this expression if we replace omega by t, we will get a new time domain signal. Okay. Okay. And in this time domain expression, we will replace t by minus omega and we will put it like this. Okay, so we will put it like this. Great. So this is duality. The duality says that if xt is a time domain signal and x omega is its Fourier transform, then in the expression of x omega, we replace omega by t, we get a new time domain signal, that is xt, and xt has a Fourier transform 2 pi x of minus omega. Okay. So this is duality theorem. So let's apply duality here. First of all, delta t. Do you remember what is a Laplace transform of delta t? Yes, delta t Laplace transform is 1. Okay, and its ROC is entire S plane. Okay, so it's absolutely summable or absolutely integrable signal. So simply we can say that its Laplace transform is 1 and its Fourier transform will also be equal to 1 because we will replace S by j omega in the Fourier transform. Now in this expression we don't have any S. Here we don't have any S. Now since we don't have any S, so there is no place to replace S by j omega. So this itself will be the Fourier transform. So delta t has Fourier transform 1. Now for 1, if we take this and we replace it, we apply the Fourier duality. So duality says that in this expression replace omega by t. So in this expression here we don't have any omega. Okay, so directly it will come here as 1 and delta t will become 2 pi del minus omega. So using duality we can say that if 1 is a time domain signal, then 1 has Fourier transform 2 pi del minus omega. Okay, 1 has Fourier transform 2 pi del minus omega. Okay, 1 has Fourier transform 2 pi del minus omega. Okay, now the point is this duality helps us in finding the Fourier transform of signal 1. 1 is a DC signal which is from minus infinity to infinity, it is a constant. From minus infinity to infinity it is a constant signal, and we can say that 1 has Fourier transform 2 pi del of minus omega. Now what is del of minus omega? Now since del t or del omega is a even signal, because del of minus omega, do you remember what is del of minus omega? So let me help. So we know that del at is equals to 1 upon mod a del at, del t, 1 upon mod a del t. So del of minus omega will be equals to 1 upon mod of minus 1 del of omega, that is equals to del omega. Okay, that is equals to del omega. Okay, now we can say that del of minus omega equals to del omega. So finally we can say that one has Fourier transform 2 pi del omega. So you have to remember this result because this result is very important. Okay, now here we can see that one is a power signal. Okay, we cannot apply the formula for finding the Fourier transform of power signal. Rather, we have applied duality. This theorem, duality says that xt has Fourier transform x omega, then x of t, capital Xt will have Fourier transform 2 pi x of minus omega. Okay, so this is the method to find out the Fourier transform of signal 1. Okay, it is a DC signal, power signal. Great. Similarly, we have e to power at ut. ATUT, let us say a is less than 1, a is less than 0, sorry, a is less than 0, means a is a negative number. Now since a is a negative number, this exponential will be a decaying signal, this exponential will be a decaying signal, or we can say that its Laplace transform will be sigma greater than a. Okay, so its Laplace transform will be 1 upon s minus a sigma greater than a. Now we can say that, now here we can say that this ROC sigma greater than a, since a is a negative number, the ROC of Laplace transform includes the j omega axis. Now since ROC includes the j omega axis, so the signal is absolutely integrable. Thus we can find out the Fourier transform of this signal, by simply replacing s by j omega. Okay, since the signal is absolutely integrable because the ROC of Laplace transform includes the j omega axis, so we can say that e to power at ut has Fourier transform 1 upon j omega minus a. Now apply duality here. The duality says that we replace j omega by t, and here we replace t by minus omega and multiply it by 2 pi. E to power minus a omega u of minus omega. So if anywhere you observe this kind of time domain signal, then this will be the Fourier transform. Okay, this will be the Fourier transform using duality. So always remember that 1 upon jt plus a minus a, any kind of this kind of signal, then its Fourier transform will be this. Apply duality to find out the result. So duality is one of the most important property of Fourier transform. Okay, great. Let's move on. Before moving to this signal, let us complete this. Suppose e to power minus mod a t, e to power minus a mod t, this is a signal. Okay, so this signal, first of all, let us see, is it a decaying signal? Yes, this will be a decaying signal, both sides it will decay, because this will be written as e to power minus at ut plus e to power minus plus at u of minus t. So right sided and left sided, we will write it like this, right sided and left sided. Now we will find out the Laplace transform, and let us see that does the Laplace transform ROC contains the j omega axis. If it contains, then this is an absolutely integrable signal. We can simply write the Fourier transform by replacing s by j omega in the expression. So first of all, let us find out the Laplace transform. The Laplace transform will be 1 upon s plus a okay, and sigma greater than minus a, okay. Now here this will be minus 1 upon s minus a sigma less than a, okay, sigma greater than minus a and sigma less than a. So here we have taken a as positive, a is positive, okay. So now we combine them and we can see that there is a valid ROC, there is a valid ROC, yes, and since a is positive, the ROC contains the j omega axis because it is from some negative value to some positive value. So we can say that the Fourier transform will be, simply replace this by j omega. The Fourier transform will be 1 upon j omega plus a minus j omega plus a minus okay, so minus 1 upon j omega minus a, okay. So if we combine these two, we can easily get the result, So now let us combine these and we can get the result, that is minus 2a upon omega square, this will come out to be plus a square, this will be the result. 2a upon omega square plus a square, this will be the result, okay, this will be the result. So now let us apply the duality here and get one more result, very important and result for this. So the result will be, so the result is e to power minus mod a mod t has Fourier transform 2a upon a square plus omega square. Now apply duality. We replace omega by t here. So we'll get 2 pi e to power minus a. We replace t by minus omega. That is 2 pi e to power minus a mod of omega. So this is the result that we have got. Okay. So this is the time domain signal and this will be the Fourier transform 2 pi e to power minus a mod omega. Okay. So this is also one of very important results. Okay. Now let's come back to a few slides which I have skipped. This slide. So you have to remember this. This signal is something like the Gaussian curve. Okay. So e to power minus pi t square has Fourier transform e to power minus pi f square. So you can remember this result. If there is any change here, we can make changes here also by using the properties of Fourier transform, that is time scaling and other properties. Okay, this I will tell you. Okay, and ut. So these three results you have to remember. Okay, remember these three results. These three are very important results. That is e to power minus pi t square has e to power minus pi f square as a Fourier transform. Signum t has Fourier transform 2 upon j omega. We will use this in Hilbert transform. Okay, and ut has the Fourier transform. Since ut is not absolutely integrable, we cannot use the formula. Neither we can simply replace s by j omega in the Laplace transform because it is not allowed, because this is not absolutely integrable. So ut will have the Fourier transform 1 upon j omega plus pi del omega. Okay, 1 upon j omega plus pi del omega. Okay, so ut has Fourier transform 1 upon j omega plus pi del omega. Now let's come on to this rectangular signal. This also result is very important. Here we will apply duality also. So duality is also very important, one of the most important duality of this result. So let us first of all solve it. Okay. So do you remember the rectangular signal we studied in class 1 or 2? The rect signal or the triangular signal. So this is a rectangular signal. The rectangular signal is, we can say that this signal is from minus t naught to t naught. This signal is from minus t naught to t naught. Okay. Minus t naught to t naught. As we can say here, it is 2 t naught and height is capital A. This is the time domain signal. So the Fourier transform x omega will be equal to minus t naught to t naught capital A e to power minus j omega t dt. We can use the formula directly because this is absolutely integrable signal. So we can apply the formula, no issues in that. So when we integrate this, we will get A upon minus j omega. Okay. And now we put the limits. Okay, we put the limits and now we can see that it is e to power minus j theta minus e to power plus j theta. This will become sin theta something. Okay, we multiply divide by 2 and we get the result, that is 2a upon omega sin of omega t naught. This is the one of the most important result. No need to remember it because by simple integration we can get this result. Okay, there is no need to remember this result. Now we need to remember the duality of this result. That is important. We need to remember the duality of the result. So the result was a rect of two by t naught, a rect of a rect of t by 2 t naught. The Fourier transform is 2a upon omega sin of omega t naught. Okay, this one. Now apply duality. The duality says that if we replace omega by t in this expression, 2a by t sin of omega t naught t naught, the result will be replace 2 pi a rect of तो यहाँ पे हम क्या करेंगे बच्चों, t की जगह माइनस ओमेगा पुट कर देंगे अपॉन 2 t नॉट। और क्योंकि आपने देखा है बच्चों रेक्ट इज अ इवन सिग्नल, ठीक है ना, रेक्टेंगुलर सिग्नल इज अ इवन सिग्नल। ओके, सो सिंस रेक्टेंगुलर सिग्नल इज अ इवन सिग्नल, we can replace this minus omega by omega itself, right? So the result will be okay, so this one 2 pi a rect of omega by 2 t naught. Okay, so now if we compare the result, this is the time domain signal, this is the Fourier transform, we can cancel this 2 and 2, we can take this pi down. So this result you have to remember in your mind always, because this is one of the most important result and many a times GATE has asked question on this result, like not less than 10 times they have asked. If we combine electrical and electronics, they have asked more than 10 times the questions on based on this result. Okay, so the result is if we take this pi down, we get a upon pi t Sine of 2 t naught has Fourier transform a rect of omega by 2 t naught. Okay, this is the Fourier transform. Okay, so let's see one or two examples on this. So if we have 5 sine of 200 pi t upon pi t, the Fourier transform will be, so just compare the results, compare this with the result. Here it is a, here it is a. So we can say that a is 5, great. A is 5, okay. This is t naught, the term with variable t is t naught. So this is t naught, 200 pi is t naught. So this will be rect of omega upon 2 t naught, omega upon 400 pi, okay, omega upon 400 pi. So we can see that this Fourier transform will be a rectangle from minus 200 pi to 200 pi, height is minus 200 pi to 200 pi, height is 5.0. Great. Okay, so this is the result that we have got. Always remember this result. Two very important points are these. Many a times it is written as sinc x, sinc x. There are two types of signals, sinc and sampling. So sinc x is equal to sin pi x upon pi x. Okay, and the second is sampling function, sampling x is equals to sin x upon x, sin x upon x. Okay, so sampling function and sinc function, these two are functions, these are very important, remember them. Whenever in GATE exam it is written as sinc x, so write it as sin pi x upon pi x and remember this result. Okay, so this is a very important result. Okay, let me combine before like moving on. Let's use the result for sinc also, sorry, Signum function also. Let's use the result for Signum function also. Then we will combine all these. Okay, so the Signum function says that Signum t has Fourier transform 2 by j omega. So if you apply duality, 2 by jt has Fourier transform 2 pi Signum of minus omega. Now if we recall the Signum function, if you know the Signum function is like this. Signum x or Signum t is like this. This is Signum x or Signum t, any function, Signum x. This is 1.0 here, this is minus 1.0. So this is a signal which is 1 for x greater than 0. It is minus 1 for x less than 0. Okay, so we can see that this is an odd function, So Signum of minus x will be equal to minus times of Signum omega. So this will be minus times of Signum omega. Okay, minus times of Signum omega, minus times of 2 pi Signum omega. Okay, so remember this result. These results are very important using duality, because in exam if you have to find out the Fourier transform of this signal, you will not be able to find it out because this integration will be very complicated. So you have to remember the result. There is no other option available. Okay, so whenever any signal is like this, 1 upon jt. So 1 upon jt, you recall the Fourier transform of Signum t and apply duality. Okay, so this is related with Signum. I'm just writing the format. Okay, you just have to remember the that it is coming from duality. 1 upon a square plus t square. So again this has duality e to power minus mod a t, something like that. Okay, so this has duality 1 upon jt minus a, this also has duality. Okay, next this one, a sine of omega naught t divided by pi t. This also has duality. So whenever you see these kind of time domain signals, always recall that this is related to duality. Okay. Now, for example, we have any signal xt. Okay, xt has x omega Fourier transform, but x omega Fourier transform also has two things, that is magnitude spectrum and phase spectrum. So let me tell you that. So there are three things: frequency spectrum, magnitude spectrum, and phase spectrum. So if xt is any signal e to power minus at ut, it is given that a is greater than 0. So this is a decaying signal, absolutely integrable signal. The Fourier transform will be, or Laplace will be 1 upon s minus a, 1 upon j omega minus a. So this is your x omega, and this x omega is called the frequency spectrum. Okay, this x omega is called the frequency spectrum of the signal. Now if we take the mod of this, it will become the magnitude spectrum, and if we take the phase of this, it will become the phase spectrum. Okay, so if we take the mod of this magnitude, so we know that how to find out the magnitude of any complex number, that is under root of real part ka square plus imaginary part ka square. Okay, so this is your magnitude spectrum. Magnitude spectrum. And what about the phase spectrum? Phase spectrum means angle of x omega. So we can see that the angle of the denominator will be, we can say that this is going in second quadrant. Okay, real part is negative and imaginary part is positive, so this is going in second quadrant. So the phase will be pi times pi minus tan inverse omega upon a, but this will be the phase of the denominator. Whenever the phase goes from denominator to numerator, we put a minus sign. Okay, put a minus sign. This is the phase of x omega, this is the angle of x omega. Okay, great. Now, so we have found the Fourier transform of this signal. We have seen what is magnitude spectra and what is phase spectra. Magnitude spectra is the magnitude of the x omega. Okay, and phase spectra means simply find out the phase of x omega, that is phase spectrum. Okay, so we have already seen this. Okay, now let's move on to the properties of the Fourier transform. Now first of all, I'd like to ask that how many students remember that that chart that we have drawn in Fourier series, that real signal has Fourier transform, Fourier series conjugate symmetric, imaginary signal has conjugate antisymmetric, and so on. So if you remember that chart, that complete chart is coming out here also. We'll draw it, don't worry. So first of all, the first property is time reversal property. So it's a very simple property. So if xt has Fourier transform x omega, then x of minus t will have Fourier transform x of minus omega. Great. So xt has Fourier transform x omega, x of minus t has Fourier transform x of minus omega. Okay, great. So using this property, we can say that, we can conclude that if xt is real, if xt is even, if xt is even means xt is equals to x of minus t. If xt is even, so we can say that if xt is even, xt is equals to x of minus t, then using this property we can say that x omega will be equals to x of minus omega. So we can say that if xt is even or the signal is even, then Fourier transform is also even. Okay, So this says that if signal is even, if xt is even, then x omega is also even. Okay, x omega is also even. Okay, now second point. Second point is if xt is odd, then Fourier transform is also odd. Okay, so if xt is odd, then Fourier transform is also odd. So these two are the properties. For even signal, we have even Fourier transform. For odd signal, we have odd Fourier transform. Okay, so this property you can remember. This is important property. Okay, now let's move on to the next thing. Second property is conjugation in time. So this property says that if xt has Fourier transform x omega, then x conjugate t, means conjugation in time, will have Fourier transform x conjugate minus omega. Okay, so use of this property or application of this property is this, that if xt is real, if any signal is real or any value is real, then the value or the signal is equal to its conjugate. So if xt is real, then xt is equals to x conjugate t. So from this property we can say that x omega will be equals to x conjugate minus omega. Now if you remember this property or this equation, we have seen this equation in chapter 1. This equation means x omega equals to x of minus omega conjugate, that is the Fourier transform is conjugate symmetric. And similarly we can say that if xt is imaginary, then we can say that xt will be equal to minus times of its conjugate, and thus from here we can say that minus times of x conjugate minus omega. So we can say that the Fourier transform is conjugate anti-symmetric. Fourier transform is conjugate anti-symmetric. Okay, so the property is real signal has Fourier transform conjugate symmetric, imaginary signal has Fourier transform conjugate anti-symmetric. Okay, great. So these two are the properties that we can see from here. Okay, conclusions. Now if we combine all these properties together, like the two properties that we have seen right now, we can get the same chart that we have drawn in Fourier series. Okay, the same chart that we have drawn in the Fourier series. That chart is like this. So the type of signal and the type of Fourier transform. The type of signal and type of Fourier transform. So signal is real. The Fourier transform is conjugate symmetric. The signal is imaginary. The Fourier transform is conjugate anti-symmetric. The signal is conjugate symmetric. The Fourier transform is real, and the signal is conjugate anti-symmetric. The Fourier transform is imaginary. Two other things that we have already seen is even signal has even Fourier transform and odd signal has odd Fourier transform. Exactly same table we have seen in Fourier series. I hope you are able to recall that table. Okay, now the next is the signal and Fourier transform. Signal and Fourier transform. So the signal and Fourier transform says that If the signal is real and even, the Fourier transform is also real and even. The signal is real and odd, the Fourier transform is imaginary and odd. It is imaginary and even, so it is imaginary and even. Imaginary and odd, it is real and odd. These are the properties that you have to remember. Okay, you have to remember these properties. And the last one is if xt is real, if any signal is real, okay, and xt has Fourier transform x omega, then even part of xt will have Fourier transform real part of x omega. Okay, even part of xt has Fourier transform real part of x omega, and odd part of xt will have Fourier transform imaginary part of x omega. Okay, great. So these are the properties that we have to remember or recall whenever it is required. Okay, so this whole chart, we have seen the exactly same chart, this whole chart in the Fourier series also. Okay, great. So this is a signal, this is a question based on the above properties. Okay, so let's solve this question. This kind of question can come in GATE exam, where the Fourier transform is given and we have to find out the property or the type of the signal. So if we look at A part, it is given that x omega is equals to u omega minus u of omega minus 2. So we can see that this will be a rectangle from 0 to 2. This will be a rectangle from 0 to 2, height 1. So we can see that this x omega is neither even nor odd, because this is present only at positive values of omega. This is neither even nor odd, but this is real. So we can say that this x omega is real, but neither even nor odd. Now since it is real, we can say that the time domain signal will be conjugate symmetric. Okay, it is real, so but neither even nor odd. So we can say that the time domain signal is only conjugate symmetric, no other property will be there. Now let's see the second one. The second one is cos of 2 omega sine of omega by 2. Cos of 2 omega sine of omega by 2, this one. So we can see that this is even term and this is odd term. Okay, so even into odd is always odd. So we can say that the Fourier transform is odd first. Second, this is also real, this is also real. So we can say that the Fourier transform is real. So x omega is real and odd. X omega is real and odd, but time domain signal will be, so time domain signal will be imaginary and odd. Okay, from the table we can say that when the Fourier transform is real and odd, the time domain signal will be imaginary and odd. Okay, great. Now let's move on. Third point, this one, C part. Okay, C part, we can see that the Fourier transform has magnitude and phase. So the magnitude is sine of 2 omega upon omega. This is the magnitude, and the phase is two omega plus pi by 2. So how to find out the result? So we know that whenever we have magnitude and phase, we can combine them and we can create the Fourier transform. So the Fourier transform will be sine of 2 omega upon omega e to power j 2 omega e to power j pi by 2. So we have to find out the time domain signal. Okay. Now we can see that this e to power j omega, first of all let us see what is sine 2 omega upon omega. Now from the previous part of the lecture, okay, we can see that rectangular signal has this kind of Fourier transform. The rectangular signal has this kind of Fourier transform. So rect of t by tau has Fourier transform 2a upon omega. Okay. So we can see that tau by 2 is equal to 2 and 2a is equal to 1. 2a is equal to 1. So we can say that sine of 2 omega upon omega will be in time domain 1 upon 2 rect of omega by 4. Okay, great. So here we have e to power j pi by 2 and e to power j 2 omega. So e to power 2 j 2 omega means shifting in time domain. Okay, we will see the property. The next property is that only. So shifting in time domain, sorry, t by 4, not shifting in time domain. So if we do the shifting in time domain, so we'll get e to power j 2 omega sine of 2 omega upon omega. So we can see that this is equal to this time domain signal. Okay, but we have e to power j pi by 2 multiplied here. E to power j pi by 2 is j only. Okay, e to power j pi by 2 is only j. So we'll multiply j here. We multiply j here. So now if we draw this, time domain signal, what is the time domain signal? The time domain signal is 1 by 2 into j rect of t plus 2 by 4, t plus 2 by 4. Now if you recall the rectangular signal, then we can get the results very easily. This will be the time domain signal which will be only from, just recall the properties of the rectangular signal. This will be from 0 to minus 4, okay, and height will be 1 upon 2 j. So we can say that this signal is completely imaginary signal. Okay, we can see that this signal is completely imaginary signal. Okay, and it is neither even nor odd, and the time domain signal is completely imaginary and neither even nor odd. Okay, great. Now the last one, 1 upon 2 to power mod k sine of omega minus k pi by 4. So let's do this also. So the last one is, the d part is x omega is equals to summation 1 upon 2 to power mod k del of omega minus k pi by 4. Okay, k equal to minus infinity to infinity. So we can see that this will be a impulse train. Okay, this in omega domain, this is an impulse train. The impulses are present at omega equal to 0. The impulses are present at omega equal to 0. Okay, k equal to 0. If you put k equal to 0, we will get a impulse at omega equal to 0. Okay, we will get the impulse at omega equal to pi by 4. We will get the impulse at omega equal to 2 pi by 4. Similarly, we will get the impulses at minus pi by 4, minus 2 pi by 4, and so on. And we can see that the area of these deltas is 1 upon 2 to power mod k. So we can see that this is completely even signal and this is real also. All the numbers are real. So we can see that x omega is even and real. So since x omega is real and even, so the time domain signal will also be real and even. Time domain signal will also be real and even. So this is all done, all 4 parts are done. So like this, if you remember the properties of that chart, then you can easily solve the questions. Okay, now let's come on to the other properties. If you recall the time shifting property of Fourier series, we remember the concept that in time shifting the effect goes with the opposite sign. So the same concept is used here also. The same concept is used here also. The effect goes with the opposite sign. The effect goes with the opposite sign. So what is this? If xt has Fourier transform x omega, then xt minus t naught will have Fourier transform x of omega e to power minus j omega t naught. The effect goes with the opposite sign. Okay, the effect goes with the opposite sign. So x of t minus t naught is x of omega e to power minus j omega t naught. Great. Time scaling property. Time scaling property is also very important. Okay, time scaling property we have seen in Laplace. So if you remember the Laplace property, the same property is repeated here itself. The property says that if xt has Fourier transform x omega, then x of at will have Fourier transform 1 upon mod a x of omega by a. This is the property. The exactly same property we have seen in Laplace. So if you link it with Laplace, you don't have to remember this property. Okay. Next is shifting in omega domain. Now this property is important. So next is the shifting in omega domain. Now this property is very important because let me tell you, let me explain it with the help of example. First of all, let us see the property. Okay, the property says that shifting in omega domain. Do you remember this? The effect goes with the opposite sign. Okay. So the property says that if xt has Fourier transform x omega, then if we do the shifting in omega domain, so here we have omega minus omega naught. So we put the we get the result in okay. Now similarly, if we shift it by plus omega naught, we get the result like this. Okay, so these are the results. The effect goes with the opposite sign. Okay, the effect goes with the opposite sign. So why this property is important? Let me tell you with the help of example. So the example says that we know that one has Fourier transform 2 pi del omega. Okay, the one has Fourier transform 2 pi del omega. So if we do the shifting in omega domain, that is 2 pi del of omega minus omega naught. Okay, so the effect will go with the opposite sign. Here we'll get e to power j omega naught t. 2 pi del of omega plus omega naught. This will go with e to power minus j omega naught t. Okay, so these are the results which are very important. If you remember, if you recall, if you remember, then the Laplace transform of these signals are not available. The Laplace transform of 1 or DC signal is not available. Laplace transform of e to power j omega naught t is not available. E to power minus j omega naught t is also not available. Okay, but Fourier transform is available. So this property is very important because if we look at the Fourier transform of cos omega naught t, so cos omega naught t is equals to e to power j omega naught t plus e to power minus j omega naught t divided by 2. So the Fourier transform will be pi del of okay, this will be the result. Similarly, if we have sine of omega naught t, it will be e to power j omega naught t divided by 2j. So the Fourier transform will be, if we put the result from the previous slide here, we'll get pi upon j okay. So this will be the result, the Fourier transforms. Okay. Now let's move on to the next property, that is differentiation in time. Differentiation in time properties is exactly similar to that of the Laplace transform. So if xt is having the Fourier transform x of omega, differentiation in time domain, in Laplace we simply multiply s here, okay, s of xs, x or s of xs. So this will be j omega times x omega. Okay, exactly similar to that of the Laplace. Okay, s of xs means j omega into x omega. Now differentiation in omega domain, this property is also similar to that of the Fourier Laplace transform. The property is like this: if xt is having Fourier transform x omega, then differentiation d by d omega x omega, the time domain signal will be minus jt xt, okay, minus jt xt. Okay, just remember these properties, these are very important. Okay, I have one chart or revision chart also for these properties. Convolution in time domain. Convolution in time domain, the property is exactly similar as that of the Laplace transform. Okay, so what was the property? The property was xt convolve ht means multiplication in Fourier domain. If we convolve the two signals in time domain, the result will be the Fourier transform of the convolved signal will be multiplication of the Fourier transform of xt and ht. Okay, that is x omega and h omega. Okay, so this is the convolution in time property, and the last is the Parseval's theorem. The Parseval's theorem says that if xt is having Fourier transform x omega, then energy of xt is equal to, the energy of xt is equal to 1 upon 2 pi minus infinity to infinity magnitude of x omega d omega whole square. Okay, this integration, this Parseval's theorem is also very important. You need to remember this property also. Okay, this is very important property, that is energy of xt was the energy signal. So energy of xt is equals to 1 upon 2 pi minus infinity to infinity x omega mod square d omega. So suppose we have to find out the energy of this signal. Okay, so in these questions the Parseval's is used. This is electronics 2016 1 mark problem. Okay, so here we will use the Parseval's theorem. Okay, so if you remember, sine of 4 pi t upon pi t 1 upon 4, the Fourier transform is 1 upon 4 rect of omega upon 8 pi. Okay, 1 upon 4 is a constant term, sine 4 pi t upon pi t, sine of rect of omega upon 4 pi 8 pi. Okay, so this, the Fourier transform is a rectangle from minus 4 pi to 4 pi. Height is 1 by 4. So the energy of the signal as per the Parseval's theorem, it is equal to, energy of the signal is equal to 1 upon 2 pi integration of the Fourier transform square d omega. So we can say that the result will be equal to 1 upon 2 pi minus 4 pi to 4 pi. Now square of the Fourier transform means 1 upon 4 square, that is 1 upon 16 d omega. So if we integrate this, we'll get 1 upon 16 into 8 pi divided by 2 pi. So the result will come out to be 1 upon 4. Okay, great. So this is the result, and like this many questions are asked in GATE exam. Okay, so this is the Parseval's theorem. These are all the properties that I have clubbed together for revision: time scaling property, time shifting property, frequency shifting property, okay, differentiation, integration, okay, all these properties are there. Okay, so from here you can revise all the properties. So in this part we have completed the Fourier transform of some major important signals. The properties of Fourier transform is also completed. Okay, great. In the next part we will be doing the system analysis using Fourier transform. Thank you. Bye bye.